Hello friends, today we are going to discuss about the dipole antenna. This is Hidayat Basha from R.M.K College of Engineering and Technology in the EC department. Now what is dipole antenna? So if you think about the dipole antenna, the simplest form of the dipole antenna is called as the half-wave dipole antenna. The half-wave dipole antenna is also called as the half-wave doublet, right? In the length of the half-wave dipole antenna, the name itself is telling that the length of the half-wave dipole antenna is lambda by 2, where lambda is the wavelength, right? And the directivity of half-wave dipole antenna, this has to be remembered so that the problems can be solved on the dipole antenna. So the directivity of half-wave dipole antenna is 1.64, and the directivity of the infinitesimal element or the antenna is 1.5. Right, now we see how a dipole, now the basic dipole, when it will be radiating the electromagnetic fields, right? So when we see that the positive charge and the negative charge with the distance is called as a dipole. Now if that particular positive charge and the negative charge are displaced at a distance, the electrical field, now the blue lines which we see in the figure, these are the blue lines and these are the electrical fields, and based upon the strength of the positive charges, it will be having the electrical field distributed all around, and it will be distributed from the positive charge to the negative charge. Now here, when this particular dipole will be radiating, now if this particular, now when the charges completes one particular, that means when the distribution of the charges complete one complete cycle of signal, then it will distribute, that means it will radiate the electromagnetic fields. Dipole, right? This is the dipole which is completing one complete half-wave cycle, and it is radiating the charges, right? That means the condition here is the signal has to exactly complete one cycle, and then only it will be radiating the signal to the outer field, and it will be acting as and even as a receiver. Now the antenna as a transmitter. Similarly here, instead of the positive charge and the negative charge, now if we can maintain like an dipole with a particular conducting wire of rod, right? Now this place, now this is the place where we have, this is considered as a positive charge, and now, so as I was telling that it has to complete one cycle, that means here the voltage, now this is the representation of that, where it has to, this particular voltage, this positive charge and the negative charge, this will be complete, right? Now whenever that is one cycle is completed, and then we can see this will be reversed again. So we will be having that positive negative and positive negative getting displaced, right? So this will be the voltage distribution, and this will be the current distribution, right? So, and now this is the lambda by 4, actually this is the length of the half-wave dipole antenna which has been taken in this topic. Now this is the half-wave dipole antenna, where we can see the total length of the dipole antenna is lambda by 4, and exactly it will be divided into two halves. So one half, that means lambda by 4 for either the positive or negative, whatever we give, and similarly another half lambda by 4 for the other conducting wire, right? And the radiation resistance, if we can note, this is only one important parameter of the antenna, the radiation resistance, which will be formed at the center of the antenna, and it will be maximum, it will be giving some maximum radiation resistance during its resonance state, right? For half-wave dipole antenna, the radiation resistance is 73 ohms, and this is to be also remembered. This is a fixed value for the half-wave dipole antenna, right? So as I told you, we are just discussing about the radiation resistance. So the dipole, the half-wave dipole has an impedance of 73 ohms at its center, which is called as its radiation resistance, right? So here we can see that, and an antenna which appears as a resistor to the transmitter, right, and it does not dissipate any heat. Now this is a resistor. The radiation resistance is an resistance which is being assumed, right, and actually it will be giving a certain type of noise from the antenna. Actually it is a noise, right. So we here it is an imaginary resistance which we are considering for the antenna, right, and we see that at the resonant frequency the antenna appears to be purely resistive as 730 ohms, right. So this is about the structure of the resonance resistance, the radiation resistance at resonance, right, and this is the equivalent circuit of this particular dipole, right. So next, now we go directly with the half wave dipole antenna. Now the half wave dipole antenna, now this is an balanced feed. Now as we have seen, right, in the previous video, what is balanced and unbalanced, right. It is in balanced feed where both are connecting to both the dipoles, right. These are the two dipoles we have. Next, now what we are going to derive now, we are going to derive the half wave dipole antenna, that is the electrical field and the magnetic field intensities of the half wave dipole antenna we are going to just derive now. Okay, now we will see how to derive the electric field and the magnetic field intensities for an half wave dipole antenna. Now this is the basic structure of an half wave dipole antenna, and this is the current distribution which we are drawing through the dotted line, right. This is the current distribution. Now you can see that now we are going to have this particular current, that is we are going to we derive the equation of current I of t towards the positive direction if we consider, and this is the negative direction if we consider. This is the I of t. Now we are going to see what will be the current equations of the particular dipole. Okay, now here we have to go through the transmission line equations where to derive these equations part. So we assume that the current, right, so we are going to derive this equation. Now we consider that the voltage which is being fed to the dipole antenna, half wave dipole antenna, is the peak value is Im, and if we can derive for the particular dipole antenna, so see that the positive half, that is taking z equal to 0 as the reference plane, and the positive half, that is when z is greater than 0, the current distribution when z is greater than 0 we have as Im into sine of beta into h minus z. Okay, and what is h here? Now we can see the particular dimensions. Now see that when z has been taken as a reference, so from z equal to 0 to the height of the dipole, this has been taken as h, right, and similarly to the bottom from z equal to 0 to z equal to minus h, it has been taken as h. So the length of the dipole, it has been taken as 2h, 2 times of h. Okay, and now we are going to measure the electrical field due to this particular dipole at a distance point p, right. Now we consider that the distance from the dipole antenna to the distance point p is from this origin as r, right. Now here it is in vector when we calculate, so we are going to just draw a parallel lines from the point to that from the point, that is from the center to the distant point, and even if we are going to have an infinitesimal element along dz, right, along z axis, if we assume an infinitesimal element dz, so from this point we are going to measure the distance. Now this distance has been taken, that is the distance from the infinitesimal element to the point p has been taken as capital R, and this is like r minus z cos theta, right, where theta is right here it has been taken as psi. So if we can just have where psi is the angle of inclination from the particular point, that from the point origin point to the point p, right. So this is the distance being covered from the infinitesimal element. Now we calculate what is the I value and that is, now this is actually, this is the I value, that is your current distribution towards your when z is greater than 0. So we right, this is the value of I when towards the dipole when z is greater than 0. So that is as Im into sine of beta into h minus z. Now what is beta? Beta will be as 2 pi by lambda, right? Similarly, when z is less than 0, so the current distribution is Im into sine of beta h plus z. So the difference here, it will be on the positive as h minus z, and at the bottom it will be like h plus z. Okay, so if you can see the figure, so the h we will be calculating from minus h to 0 and 0 to h, right? So will be from minus h to 0 and from 0 to h with the same components. Now here we have to substitute the value of r, and if we can able to get the equation, right, if we can able to derive Az equation, so we will be getting the magnetic field intensity, that is the magnetic vector potential, right? If we just simplify this integration part, and by substituting h equal to lambda by 4, actually we know that h is the value of length is 2h, and so we will be getting the length, the total length will be like lambda by 2.